So title of my talk is Bridging Induced Coil-to-globule transition. Here coil-to-globule is the structural conformational structure of the polymer. So transition from coil kind of structure to globule kind of structure in polyelectrolytes. Polyelectrolytes are charged polymer basically. So, so what are the we know about polymer conformation in different solvents I'm showing here. So in good solvent condition, monomer-monomer attraction is less than monomer-solvent attraction. We can say the polymer kind of find themselves in an extended kind of structure, and in the poor solvent condition, the polymer found themselves in a collapsed kind of structure. We are calling globule here, and these conformations scale with the number of monomer inside them as and 3/5 for a good solvent condition and 1/3 for a poor solvent condition, right? And this R is like n power mu for a different scaling exponent for good theta or poor solvent condition. But it's not always that polymer found themselves in a single solvent condition. They generally found themselves in very crowded environment. In the relevance of like biopolymers and all, in a cell there are huge crowding there, like 20 to 30% of the total volume is crowded by the particles like protein and so on. So it's really important to study polymer in a crowded environment or in presence of crowders basically. So if we have a crowder in along with the polymer or macromolecule, they can have typically two kind of interaction with the polymer or monomers. First is repulsive crowders. So they will give rise to something called depletion. When the crowder go away from the surface of the polymer and the polymer collapses and the crowder gain the translational entropy, this phenomenon is known as depletion effect. It's been explained by Osawa in 1954. And the other interaction that crowder can have is the attractive crowders, like so that will induce collapse due to the bridging. That's we are focusing on. So intuitively one would think that if the attraction between the crowders and the monomers or the polymer is increases, it should take the extended kind of form or a coil kind of form in order to maximize the surface with the attractive crowders. But non-intuitively it has been observed that the chain collapses as we increase the attraction between polymer and the crowder particles. And the reason is the single crowder particle acting as a bridge or a glue between the distant part of a single polymer to make the chain collapse. So you can see here as a single crowder is the green shows the single crowder acting as a kind of bridge between the distant part of a single polymer chain. So so there is like there is another way of this coil-to-globule transition, and this has been studied for a while now. We also did a study here for neutral polymer, which goes from a extended kind of structure as from you can see from Rg to a collapsed kind of structure as we increase the attraction between the monomer and the crowders, right? So what questions are we addressing now? So all the studies I've shown is mostly for neutral kind of polymer. Can the neutral crowders induce the collapse in polyelectrolytes, the charged polymer now? Since there is monomer is charged, so they have electrostatic repulsion between them. Can we found such kind of collapse even for with the help of neutral crowders? And if yes, what is the critical value of this monomer crowder interaction or attraction for this kind of transition? And how does the phase diagram looks like in the charge density and the monomer crowder attraction, right? So before I introduce crowder in my system, I just want to go through what polyelectrolyte does in presence of counter ion only without crowders. So we know that now it's been known that as the polyelectrolyte undergoes a coil-to-globule transition, if the charge density on the chain backbone is increases above a threshold value AC. A is basically just charge density you can consider. So below a threshold, you can see the chain is in the extended kind of structure. There's no crowder, only counter ions are there to neutralize the whole system. And as we increase the as we increase the charge density on the backbone, it goes into a collapse kind of structure. And this was explained by Manning in 1969 through Manning condensation. And there are many theories which explain such phenomena like dipole theory, counter ion fluctuation, and ionic theory, etc. But I'm not going into these things. So I'm just introducing crowders now, neutral crowder to the system. So this is our model. So very simple model with a single polymer chain, charged chain. In presence of crowder particle shows as blue and the counter ions here, and the solvent is implicit so that we don't want to take into account the solvent effect on this. And the potentials are LJ potential for all the particles, and the bonded monomers interact via the harmonic potential, and all the charges interact by electrostatic potential, right? So now what is the role of Crowder in, so we divide this into two regimes, when A is less than AC, when the chain is in the extended kind of structure, when there are no Crowder introduced. So you can see here, so we have worked with the three different valencies of the counter ions, Z equal to 1, 2 and 3, I'm showing here 1 and 3. So you can see when there are no Crowder, you can see interaction is very low with the Crowder. The chain is in the extended kind of structure, RG is in the regime of extended structure. But you can see as we increase the monomer and Crowder attraction, this epsilon MC is basically the strength of the monomer Crowder attraction. And as we increase this strength, we see there is a nice transition from a extended or a coil kind of structure to globule kind of structure here, right? And the same we saw for Z equal to 1. And even this collapse form is has a profile of Crowder inside the globule. So you can see this is rho of C, that density profile of the Crowders and the monomers. You can see at the center of mass of the chain, we see more Crowder than the monomer, right? So the Crowders are coming inside the globule to make the chain collapse. Now in the other regime, when A is greater than AC, that means chain is already collapsed due to the counter ions. There is even though the Crowders are not present. When we introduce the Crowder and increase the attraction, but we see there is a slight increase in the conformation, but not much, and then again goes to a collapse regime. So it going from a new initial collapse regimes to a new collapse regime, but they are two different collapse regime in structure wise. So you can see here the profile of the Crowders. So this R equal to 0 means the center of mass of the chain, and we see when the attraction is very low, the 0.1 blue, there are no Crowder inside, right? And as the attraction is very high, that is 4, for example, the strength, we see that now the Crowder occupying the internal part of the globule. So even though these two are the same, two are the collapse form, but they are totally different in the sense of the Crowder arrangements. So this is our phase diagram looks like. So Z equal to 3 and 1. So we primarily find three different phases. C is the extended kind of phase when there are no Crowders or less attraction with the Crowder and less charge density. As we increase the charge density, we see a CCI phase, that is induced phase due to the counter ions, and then CCB, that is the collapse induced due to the bridging neutral Crowders, right? And this has been observed for all valencies that equal to 1, 2 and 3. It was the same we got for neutral polymer as well, which we did earlier in 2023. And what was fascinating was in Z equal to 1, there is a strip here for the high value of epsilon MC, that means high value of attraction with the monomer and the Crowder. We do not see any bridging induced collapse at intermediate value of A. And the reason was the steric hindrance. So what is happening, the neutral Crowder has to replace the counter ion in order to collapse the system. Because of the size of the Crowders, they are it was difficult for Z equal to 1. But so idea was if we reduce the size of the Crowder, we should see the collapse here as well. And that's what we found as well. So here we reduce the size of the Crowder by half, and we see now the RG belongs to a collapse kind of regime, right? So these are the conclusion that the attractive Crowder induced this CC transition in polyelectrolyte. Even the monomer are electrostatically repulsive. The neutral Crowders are quite effective to induce this collapse. And this soft interaction, that attractive Crowders can give rise to this CC transition at very lower density compared to what we got from the depletion kind of effect, where we need a quite high density or a lower Crowder sizes. And these critical transition points are quite strict function of what charge density we work with. With this, I would like to thanks. These are the reference and these are the acknowledgement. So my supervisor Satyavani and R. Rajesh, and this in my collaboration with Kamal Tripathi. Thank you.
Questions?
Hi. So with different interactions, you see this change from coil to globule by just looking at the RG value.
Yes.
Right. So this can come from the change in the prefactorial, let's say, like, your Kuhn length or the persistent length as well. Did you also look into the conformational statistics, for instance, with the number of monomers, how does it scale and so on?
Yes. So this is totally flexible polymers. there is persistent, no persistent length as such. But we also look at the regimes that I showed in the first slide, that Rg goes as 1/3 with the monomers in the pore solvent. So all of them, what we are calling as a like poor collapse regime, we scaled with the different monomer sizes, and these all are collapsing with the single thing. Yeah, you can find these in the manuscript itself. All of them are being scaled with the 1/3 for a pore solvent condition.
Any other questions?
So you're considering charged polymers, right, with
Yes.
the polyelectrolytes. And the Crowders, are they charged? Or
No, they are neutral.
How do they actually interact with the polymer backbone at all? And if
Oh, they have an LG interaction with them, a Leonard-Jones interaction. This LG interaction.
But that cannot be very strong, right?
Yeah, still they are able to. So in the first study we did for the neutral polymer also, and there also we have a Crowder, neutral Crowder, and they were inducing.
For neutral, I understand that it can still work. But in this case, so there must be some kind of, let's say, interaction epsilon. Some critical epsilon would be required to induce this kind of collapse to collapse state, right?
True. That's what we did. No? Phase diagram, we find the critical value of this attraction, which will induce. It's not the any attraction will induce.
Okay.
So in the phase diagram, we explain that, right? So going from CE to CCB, that is bridging due to the neutral Crowder, require a different epsilon MC. Here you can see. So it's not
What
independent.
is the size of the Crowder? That also should be important here.
That should be important. So that's what we are doing now. So there are some results here. So size effect we are studying. What are the Crowder sizes? We got some preliminary results here, and you can see here. So this is for neutral polymer. Same goes for the charged one. We see this is the size of the Crowders, and see showing the non-monotonic behavior with the epsilon MC. So it's quite fascinating to study these Crowder sizes as well. Because in the depletion, Crowder size matters a lot. Like if we have a smaller size, this depletion effect is very huge. So that's also we are looking at for this attractive Crowders as well.
So for the polyelectrolyte, do you consider the screen kind of interaction to take care of the charges, or you take the full Coulomb interaction?
Full Coulomb interaction. Yeah. So we use a software like LAMPS and
Okay.
tools.
Thank you.
Let us thank the speaker again.